This PowerPoint presentation is for Chapter 15.2 on Lewis acids and bases. In this video, we'll cover the definition of Lewis acids and bases, talk about complex ion formation, and look at the effect of complex ion formation on the solubility of sparingly soluble salts. At the beginning of Chapter 14, we provided several definitions of acids and bases. Up until now, we've focused primarily on the Arrhenius and Bronsted-Lowry definitions. As a reminder, the Arrhenius definition states that an acid is a species that produces the hydronium ion in water. An Arrhenius base is any chemical species that produces the hydroxide ion in water. In the Bronsted-Lowry definition, an acid is a proton donor and a base is a proton acceptor. In this chapter, we'll introduce the Lewis definition of acids and bases. A Lewis acid is a chemical species that can act as an electron pair acceptor. A Lewis base is an electron pair donor. Let's look at an example. We've already seen that the fluoride ion can act as a base. Fluoride in water will produce the HF ion and hydroxide ions. This means that fluoride is an Arrhenius base because it produces the hydroxide ion in water, and it can also be classified as a Bronsted-Lowry base because the fluoride ion in this reaction accepts a proton from the water molecule. If we look at this reaction, we see that fluoride can also fit the definition of a Lewis base because it can donate an electron pair to form a new bond. In this reaction, fluoride is our Lewis base, and it donates this pair of electrons to the Lewis acid BF3 to form the ion shown. Notice that the Lewis definition of acids and bases requires that a Lewis acid reacts with a Lewis base. Also note that although the fluoride ion can be described by any of these definitions, BF3 would only properly be described as a Lewis acid. We would not describe boron trifluoride as either an Arrhenius acid or a Bronsted-Lowry acid because it does not hydrolyze water and has no proton to donate. The Lewis acid-base definition is particularly useful for a certain class of compounds called complex ions. We've seen examples of complex ions already. In the equilibrium lab, we worked with the complex ion FeH2O5SCN2+, also known as the penta-aqua thiocyanidal iron 3 complex. And we also saw how complexes of metal cations with water, like the cobalt complex shown, can act as acids by donating a proton. A complex ion is defined as an ion formed from a metal cation and one or more ligands that have a lone pair of electrons to donate to the metal cation to make a coordinate covalent bond. A coordinate covalent bond is formed when one atom donates both of the electrons that form the bond. These Lewis bases that attach to the metal cation are also called ligands. So in this example, the water molecules are the ligands. And it's the lone pair of electrons on the oxygen atom that is donated into the metal cation center to form each coordinate covalent bond. We will cover these types of compounds, including their names, in more detail in Chapter 19. The following species tend to form complexes with transition metal cations: ammonia, cyanide, and iodide. Let's take a moment to draw the Lewis structures of these species and see what feature they share that makes them good Lewis bases and good complexing agents. So ammonia has a total of 8 valence electrons. The nitrogen atom will be in the middle. The 3 hydrogen atoms will be attached to the nitrogen, and the nitrogen has 1 lone pair of electrons. The cyanide ion has 10 valence electrons, and its Lewis structure is formed having a triple bond between the carbon and the nitrogen and a negative formal charge on the carbon. Iodide, of course, has 8 valence electrons. So these are the Lewis structures of these 3 species. What feature do they share? They all have lone pair electrons that can be used to form coordinate covalent bonds. The formation of complex ions is another class of reactions that fall under equilibrium conditions. We can now define a new equilibrium constant. We'll call it Kf. That stands for formation constant. Kf is the equilibrium constant for the reaction that forms a complex ion. The example shown is for the formation of the diamine silver 1 complex from silver ions and ammonia. The Kf for this reaction is, as before, product concentrations over reactant concentrations. The table shows some values of Kf for different complex ions. Remember that these numbers actually represent equilibrium constants for a specific chemical reaction, namely the reaction that forms the ion shown. Note also that these K values tend to be rather large, indicating that these reactions are product favored. We mentioned in a previous video that certain metal cations would show increased solubility at high pH. This chart helps explain that. Aluminum, for example, is able to form a complex ion with hydroxide. The Kf for this reaction is quite large. This means that if there is sufficient concentration of hydroxide ion in solution, this soluble complex ion will form, bringing the aluminum ion into solution. Which other metals show this behavior? The cobalt 2 plus ion, the chromium 3 plus ion, lead 2 plus, tin 2 plus, and zinc 2 plus. All of these cations form complex ions with hydroxide. The formation of complex ions can increase the solubility of a sparingly soluble compound. This can be explained by Le Chatelier's principle. The formation of the complex ion reduces the concentration of the free metal cation and drives the equilibrium to the right. As an example, let's look at the solubility of silver chloride. Silver chloride is not very soluble. However, if you add ammonia to the system, you'll increase the solubility of the silver chloride. Ammonia will complex with the silver ions produced, reducing the concentration of silver ions in solution, which will drive the solubility equilibrium towards products. We've just seen that the formation of a complex ion can help dissolve an insoluble compound. We can quantify this by combining the relevant equilibrium expressions. The dissolution of a salt in the presence of an ion that can form the complex ion is the sum of the dissolution and the formation reactions. The equilibrium constant for this combined reaction will be the product of the two equilibrium constants. If the product of Kf and Ksp is greater than 1, the overall reaction will be product favored. Let's compare the solubility of silver chloride in the presence of ammonia or the presence of the cyanide ion. In the presence of ammonia, we would use the following two reactions. The silver chloride dissolution reaction, showing the solid dissociating into silver ions and chloride ions, and as we've previously seen, this has a Ksp value of 1.77 times 10 to the minus 10. If we couple that with the complex ion formation between silver and ammonia, which has a Kf value of 1.7 times 10 to the 7th, when we combine those two reactions, we get a reaction that shows the dissolution of silver chloride solid in the presence of ammonia to form two dissolved species, the silver complex and chloride ions. In this case, the K value for the overall reaction is 3 times 10 to the minus 3. So it's still not product favored, but it's a much more product favored reaction than just the solubility of silver chloride alone. What about the solubility of silver chloride in sodium cyanide? Here we would combine the silver chloride dissolution reaction with the formation of the silver cyanide complex. Here, because the formation constant of this complex is so large, when we put the two reactions together, we get an equilibrium constant that is 1.8 times 10 to the 11th, showing that this reaction is extremely product favored. And in fact, cyanide can be used to dissolve silver chloride deposits. Let's calculate the molar solubility of silver chloride in a 0.1 molar ammonia solution, and then compare that to the solubility of silver chloride in water. To calculate the solubility of silver chloride in the ammonia solution, we'll use the combined reaction that we generated on the previous slide. This reaction shows the silver chloride solid reacting with ammonia to form the ions in solution. And we saw that this reaction had a K value of 3 times 10 to the minus 3. We can set up an ice table for this reaction. We don't need to put in a concentration for the solid. We'll put in our 0.1 molar as our initial concentration of ammonia and assume 0 initial concentrations of the complex and chloride. In terms of the change row, we'll have minus 2s for the ammonia and plus s for each of the products. Our K expression is the concentration of chloride times the concentration of the complex divided by the concentration of the ammonia ion squared. Putting in our equilibrium expressions, we have s squared on the top and 0.1 minus 2s quantity squared on the bottom. Since the equilibrium constant is still rather small, it might be a good assumption to neglect the s in the difference term. If we do this and solve for s, we get that s is approximately equal to the square root of the k value, 3.0 times 10 to the minus 3, times 0.1 squared. Solving for that, we get an s value of 5.5 times 10 to the minus 3. We need to check and see if our assumption was valid. We do that by multiplying 2 times s and comparing it to the 0.1 that we neglected it from. When we do this, we find that it's about 11% of the value, so a little bit larger than we like. To fix this, we can iterate. And again, to do that, we plug in our first estimate of s into this equation to get a new value of s. Our second value of s turns out to be 4.9 times 10 to the minus 3. Plugging that back into our equation gives us a third value of s, which again is 4.9 times 10 to the minus 3. So we say that our solution has converged. So the solubility of silver chloride in the presence of 0.1 molar ammonia is 4.9 times 10 to the minus 3 molar. Let's compare that to the solubility of silver chloride in water. The KSP value for silver chloride is 1.77 times 10 to the minus 10. That should be equal to S squared. So the solubility in water is 1.3 times 10 to the minus 5. When we compare these two numbers, we see that yes, the solubility has been improved by over a factor of 100 when we add the ammonia complexing agent. We've now finished section 15.2. Try group problems 8 and 9 to test your comprehension of this material.